Hi everybody, welcome back. So today I'm making a video about truss structures, just as I promised all the time. However, this video is going to be an introduction and basics, so there will be no solving trusses with methods like method of joints and method of sections. That will be in other videos, hopefully. Today we will only look at finding the determinacy of trusses, what a truss is, and degrees of freedom. So if you don't know what these three terminologies are, determinacy, degrees of freedom, I really think you should watch the previous videos in the playlist. It's called trusses, no, statics and structural analysis. I will put it in the description if you want. Anyways, so what is a truss? Trusses are used to make many things, including bridges. Every time someone says truss, all I think about is a bridge. You see how a bridge is made, and you got like the way it's hanging, it's all because of trusses. Uh, I will show you pictures of like a proper truss structure that could be used for bridges. But let's get started. So all you will have to do is bring a bar, so a bar of metal, okay, and then you connect them to two pins, one pin on each side. Now that is just one member of a truss, okay? Then you can connect other members together. You will see how they can be connected. Now, loads can only go on the pin, okay? They cannot go, if they go on the bar, it is not a truss anymore, okay? Now, the best structures of truss is when you have them in triangulated bars. Remember, triangles are always the best shapes in maths. They are amazing, okay? Then we can have tension on a member, truss member. So tension is when your bar is, you've got two opposite forces going outwards of the pins, or you could have compression, which is the opposite. So you get two forces going this way from one pin and then to the other pin. Okay? Now, truss and anatomy. This is where we have to dig a bit deeper. What are bars? We have talked about bars, we have talked about pins, we didn't talk about supports yet. So the bars are just you see the straight lines in the picture, that is a bar. And then the pins are the small little circles. Supports, we have learned about supports in another video. You could also check that in the description if you want to watch it, or if you already know it, then that's great. So there can be in terms of rollers, pins, and incasters. I'm not going to explain what these are. I'm assuming you already know. So yes, now you could have 2D plane, a truss in a 2D plane, or 3D. Usually, well, everything is in 3D, but we simplify it, so we will learn how to do it in 2D first. And usually bridges, okay, they solve them more in 2D because you just analyze one of the vertical sides as a planar truss. Planar truss is 2D plane truss, and then it is applied as load at the pin connections. So then, because it's kind of like, think about the shape of a bridge, but things to do with airframes. So in an airplane, there's trusses. There's trusses everywhere. Whenever you build anything, there is trusses. So many things. I can't think of many examples on the top of my head, but yeah. So the picture you have here, it is a roof truss supported across a football stadium. Oh, that is another example. You've got a pin, fixed pin, on the left side and a roller pin on the right side. We haven't had any incasters here. And you could see they all forming triangles, which is great because we said we love triangles, don't we? Anything you think of in physics, maths, or engineering, there is always going to be assumptions. And here for trusses, these are our following assumptions. First one, we are going to assume there is no moments, there is no moments being transmitted on the pins. So that's the nodes and the joints. The loads are only being applied on the nodes, okay? The weight of the entire truss is going to be neglected, and we are going to think and assume that these bars are the strongest material you could ever think. They are rigid, okay? They cannot be collapsed. Now we've got some other terminologies. Sometimes I feel like no one uses these terminologies. Maybe I just think that. Chords, they are, when you look at a truss, the top members and the bottom members are called chords. Web members, you could tell from the name, they are between the chords. Struts are web members. In axial compression, ties is just the tension. Web members in axial tension. Right. Finally, some pictures. I know you guys were waiting for some pictures. You can have, there's different types of trusses, so they are used for different things. The top ones, they are roof trusses. You don't need to know these except if you're doing civil engineering. These are just examples of where you could use trusses and types of trusses. Then the bottom one is a bridge truss. You could pause the video and look more into it. Personally, I'm not going to analyze it a lot. Right. Now we get to the very important part, degrees of freedom. We really love degrees of freedom in statics, don't we? In trusses, we also have degrees of freedom. Now, one pin is equivalent to 2 degrees of freedom. 2 pins, then that will be 2 times 2, 4 degrees of freedom. Now, if you have one bar, okay, one bar is usually, one bar removes 1 degree of freedom. So we'll do, because you have 2 pins, and 2 pins is 4 degrees of freedom. You do 4 minus 1, gives you 3 degrees of freedom. You got now 3 pins and 1 bar. 3 pins, that is 3 times 2, 6. And 1 bar is 1, so 6 minus 1 is 5. Then you can have 3 pins and 2 bars. 3 times 2 is 6, 2 bars, 6 minus 2, 4 degrees of freedom. So we have the first example here. We want to find out if it is statically determinate. Now, if it's statically determinate, the remaining degrees of freedom will end up to be 0. And then we will find another example for statically indeterminate. And then we'll have mechanism. Okay, so now we're going to look at statically determinate case. This is an example. So to remind you how to find the total degrees of freedom, you get the degrees of freedom that is generated. The pins itself generate degrees of freedom. You do 2 times the amount of pins you have. Here, for example, we have 6 pins, so you do 6 times 2. Now that is 12. Then you minus away from the amount of bars you have. Let's count the amount of bars we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 9 bars. So you do 12 minus 9. 12 minus 9 gives you 3. Then you have your supports. The reactions you get from the pen, from the fixed pen and the roller pen. The fixed pen is you remove 2 degrees of freedom, and the roller pen you remove 1 degree of freedom. That means 3 minus 2 minus 1, that gives you 0. Therefore, it is statically determinate. We have example 2, which is supposed to be statically indeterminate truss, we will see how we can calculate this to end up with statically indeterminate. Remember, to have a statically indeterminate object or body in statics, we will have to have a number of degrees of freedom that is left. It should be less than 0. Let's see here. The number of pins we have are 10. You could pause the video and count them, but I just know, okay, I already counted them and I put them there. Pins are always multiplied by 2, so if we multiply it by 2, you get 20. Then you take away from the degrees of freedom of the pins, you take away from them the bars, the degrees of freedom of the bars, and the reactions. The bars, we have 18 bars. Then if we multiply that by -1, because for each bar you take away 1 degree of freedom, you end up with -18. So you will get 20 minus 18. You will have to end up with 2. However, we also have a number of reactions. We have a fixed pin and a roller pin. So the total reactions we have to remove is 3. We end up with 20 minus 18 minus 3. 2 minus 3, -1. That is less than 0. We get statically indeterminate truss. Sometimes though, if you get less than 0, it doesn't mean it's statically indeterminate. We're going to see on the next slide. You have to sometimes give like a sanity check. Look at the structure more. So example 3, we are supposed to have this example as a mechanism, but let's find out how many degrees of freedom we have left. Remember, for mechanism, the degrees of freedom should be higher than 0 to be classified as a mechanism. Here we have 4 pins, and 4 times 2 is 8, because every pin has 2 degrees of freedom. We have 6 bars. Each bar you remove 1 degree of freedom. 8 minus 6, 2. We have a fixed pin and a roller pin. Together they make 3 reactions that we have to take away. 2 minus 3, which it gives you -1. That suggests that you have to have statically indeterminate truss. However, it's not. It's a mechanism. How come? That is because sometimes you should always have to do a sanity check, especially when you have an X-braced panel like we have here. Whenever you look at this shape, you always be like, okay, so you just remember it all the time. And the reason for that is because the whole square can actually rotate and collapse. You will ask me, how come? Well, we might have a fixed pin right on the left, but we have a roller pin there. Because here we got bars and we got 2 web bars in the inside, what could happen is that it can't stay rigid, okay? The X-braced panel, it can't actually be rigid without diagonal to diagonal check. It is going to be moving. You should always remember this. So whenever you actually look at any other truss, you know if it's a mechanism or not. Let's go to the next one. Before we learn how to solve for missing forces and reactions on a truss, it's important to first learn what a zero force member is. The reason for that, because it makes your life so much easier. If you know one of the members is a zero force member, you could remove it from the truss. So what is a zero force member in the first case? It is a bar that literally carries 0 force under any given load. Whatever you put the load, it is 0 force. You will ask then, what's the point of that member if it has 0 force? It could be 2 reasons. Either because we can have different loads at different times, like an aircraft. A member, for example, could be 0 force when it is going onto the ground because of gravity. It is And then when it's flying, then you have more of, you want the drag. So then the drag will be the force on top, and then the other one will be the zero force member. I'm not gonna dive deep into it because honestly, even I'm a bit confused, as you could tell. Anyways, but the most one that you could see is stability. Sometimes, okay, you've got some members that prevent the structure turning into a mechanism. You might have a structure that where it has a member that does not have any force. You might think, okay, you could remove it. Well, when you're solving for it, you could remove it, yes, but the reason it's there is so that it doesn't move. Okay, there's times when maybe this structure could move and turn into a mechanism. We keep that bar because remember, a bar, okay, means it can take away 2 degrees of freedom. Sorry, 1 degree of freedom, okay? So if you have a degree of freedom higher than 0, which if you add a member, okay, a zero force member, it will remove 1 degree of freedom. Okay, think of it that way. So it causes it to be more stable, okay? Now, we can always usually spot them by eye, and you will see what I mean now. Now, you can have 2 bars that are connected to a pin, and there is no any external load on that pin, then obviously these members are going to be zero force. If you have 2 bars and 1 pin, and you got a load aligned with the bar 1, as you see on the pin, okay, the load is not going this way or this way, it is aligned to the bar. Then the non-aligned one, which is the diagonal one, as you see, is going to be a zero force member. What about if we have 3 bars that are connected to 1 pin, and the pin has no external load at all, no force on it? Then you get, well, depends on how it looks. If 2 of the bars are aligned, then these will not be a zero force member. It will be the one that is not aligned, the odd one out, that will be a zero force member. Now, the cool thing about zero force members is if you find one zero force member, only one in a truss, then you can, you can reveal another zero force member by removing that zero force member. You can get, it's called the domino effect. Usually when you have a truss that has like a double supports, it's like an encaster, in that case you will have 8 zero force members, and you can identify them by inspection. And then if you remove them, that will make your life so much easier. Then you can use method by section or method by joints. I'm really hoping I'll make a video about that in the future. And also something you really have to understand is you can have a truss and you put a specific load on that truss. You identify some zero force members. Great, but if we change the load, it doesn't mean these zero force members will stay the zero force members. Remember, the zero force members are there for a reason. One of them is stability, second of them, so that zero force member actually could be a zero force member at certain loads. When the load changes, then then when the load changes, another member could be a zero force member. Okay, that's all. Also, load at an angle. Just because you have force that's acting at an angle and it does not align to a bar, it does not mean there is no zero force members nearby. I really hope you enjoyed and understood the video, and you had a grasp of like what trusses are. Thank you so much. and have a very lovely day.